YouTube channel. All right, chemistry 3111. So where we left off was looking at heterocycles, pyridine and pyrrole, namely. And I told you that before the break, I told you that these two compounds are both aromatic, but they're both aromatic for very, very different reasons. And so it says here, heteroatoms other than carbon and hydrogen can also be part of an aromatic ring. So if we take a look at these two molecules, let's start by looking at pyridine. And I'm going to go over the number of regions of electron density on this nitrogen. If you remember, a lone pair is considered a region of electron density. A single bond is considered a region of electron density. And then a pi bond is considered a region of electron density. And so that means that the hybridization of this nitrogen is sp2. But what kind of orbital is the lone pair residing in? Turns out the lone pair is actually residing inside an sp2 hybrid orbital. How do I know that? Because I know that there is an unhybridized p orbital on this nitrogen, but it's involved in forming this pi bond right here. And we can't have two unhybridized p orbitals on our nitrogen. And again, therefore, the lone pair here is inside an sp2 hybrid orbital. So it's inside an sp2 hybrid orbital. And so even if I protonate pyridine, so if I use that lone pair to accept the proton, this compound is still going to be aromatic. Now, if we look at pyrrole, on the other hand, and we look at its hybridization, well, you might look at it and say, well, you know, you've got 1, 2, 3, 4 regions of electron density. And so can it participate in resonance? The answer is yes. Yes, it can. And also, what do we know? We know that if this nitrogen was to take on sp2 hybridization, and if we had this lone pair in an unhybridized p orbital, then we would have a continuously overlapping system of p orbitals. So rule number 1 would be met. And then would it be a Huckel number? Yes, it would be 4n plus 2, or n is equal to 1. So that would give us 6 total electrons. 1, 2, 3, 4, 5, 6. And so pyrrole is an aromatic compound as well. But the difference is the lone pair is involved in aromaticity, right? It's involved in that continuously overlapping system of p orbitals, whereas in pyridine, the lone pair on the nitrogen is in an sp2 hybrid orbital. Maybe I should label this here. This is a p orbital. And so it is not involved in aromaticity, which frees up that lone pair to behave as a base, whereas the lone pair on pyrrole, it can't behave as a base. If it did, then the compound would lose its aromaticity. Give me a thumbs up if you're with me 50% of the way on what I just said. Even 50% of the way if you're like, I kind of follow you. Yeah, good. So if we look at those two, okay, it says the heteroatoms lone pair, if the heteroatoms lone pair is required for aromaticity, it's going to be included in the Huckel number. So again, on the nitrogen and pyridine, it wasn't included in the Huckel number, but the nitrogen on pyrrole, it was included in the Huckel number. So if you didn't follow me on that whole thing about the nitrogen on pyridine or pyrrole accepting a proton and blah, 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 well, take a look here. If the lone pair on the nitrogen accepts a proton, okay, you end up with a pyridinium ion, and it's still aromatic. And so that's why pyridine is a base. Pyridine's a good base, okay? Why? Because when it accepts a proton, it's still aromatic. However, pyrrole is not a base. So pyrrole is not considered a base, or not a good base at least, because if it accepts a proton, then you end up with something that's non-aromatic. And that explains the huge difference in their pKa's. The reason that this thing is so acidic is because it wants to get rid of that proton to become aromatic, whereas this one is going to be much more indifferent, so it's not going to be as acidic, because when it loses the proton, it's still aromatic one way or another. So there you go, two compounds that are aromatic, but for very different reasons. Again, in the pyridine, okay, the lone pair on the nitrogen is localized, right? This lone pair is in one spot, and you can see that in the electrostatic potential map, whereas the lone pair on pyrrole is delocalized. It's participating in resonance, Why? Because it's in an unhybridized p orbital and it is participating in resonance. There you go. So that's an explanation of a couple of aromatic heterocycles. So with all that, let's take a look at some examples here, and I'll try to guide you through these because some of these it's more abundantly clear whether they're anti-aromatic, aromatic, or non-aromatic. So again, for aromatic, we're going to use A. For non-aromatic, we'll use Na, and for anti-aromatic, we'll use Aa. All righty. Let's take a look at the first one here. Okay. We take a look at the first one. We've got a continuously overlapping system of p orbitals, right? Because this lone pair can participate in resonance. Okay, so we have a continuously overlapping system of p orbitals. So number one is met. What about rule number two? Is this a 4n plus 2 number of electrons? Does this satisfy 4n plus 2? Yes or no? No, it doesn't. In fact, it satisfies 4n as a matter of fact. So it's 4n where n is equal to 1. And there's no way that I can force this molecule out of planarity because it's a three-membered ring. And so this, you'd call this the cyclopropenyl carbanion. This would be anti-aromatic. There's nothing you can do about this compound. It's going to be aromatic. Well, let's turn it around and look at B. Okay, let's go over very slowly. What is the hybridization of every single carbon in this ring? This is not a trick question. sp2, right? So every single carbon in here is sp2. Okay, so do we have a continuously overlapping system of p orbitals? Yes. Does it satisfy a Huckel number, 4n plus 2? Absolutely, right? Where n is equal to what? N is equal to 0. Good, because we have 2 electrons in the system, or 2 pi electrons is what I should have said. Therefore, this would be considered to be an aromatic ion, right? An aromatic cation. All right, let's take a look at the next one. Okay, if the hybridization, so the hybridization of every carbon in here, including the carbocation, is sp2. So we have a continuously overlapping system of p orbitals. Does it satisfy 4n plus 2? Does this satisfy 4n plus 2? We have a total of 4 pi electrons. No, it satisfies 4n, doesn't it? Where, we'll put here where n is equal to 1. Therefore, and this compound can't get out of planarity either, and so this would be an anti-aromatic compound. It's considered to be anti-aromatic. There's nothing it can do. Let's take a look at this last one here. So let's first start by looking at the carbanion. Is the carbanion going to be sp3 hybridized or sp2? Well, let's imagine that it's sp2 so that we have a continuously overlapping system of p orbitals. Let's just imagine that criteria number one is met. So if that lone pair was in a p orbital, would this be an aromatic compound? Exactly. Where n is equal to what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to be where n is equal to 2, right? N is equal to 2. There you go. And that's it. Therefore, this would be an aromatic anion. Boom. That's pretty good. That's pretty good work, everybody, answering those, okay? So what I would recommend that you do is look at the rest of these examples in the textbook and try them on your own. In the interest of time, let's try looking at some compounds here. So now we're going to be very careful here. It says for each of the following compounds, determine which, if any, of the lone pairs are participating in aromaticity. So I'm going to do this very slowly. If we look at this first compound, okay, the question you want to ask yourself is one of the lone pairs in a p orbital? Yes or no? Do you think that one of these lone pairs would it be participating in aromaticity? Tiana says yes. The reason she said yes, so I'm going to circle this in a p orbital. So we'll put here that the hybridization of this oxygen is not sp3, it must be sp2, right, Nicole? Because then you'd have a continuously overlapping system of p orbitals, right? And you would have 4n plus 2, where n is equal to 1, and therefore it would be an aromatic compound. And so the answer is, for this lone pair, yes, it is participating in aromaticity. Let's go down to the next one. If we imagine one of these lone pairs, okay, as being in a p orbital, would we have a continuously overlapping system of p orbitals? The answer is yes. Would it satisfy a Huckel number? The answer is yes. It would be 4n plus 2, where n is equal to 1. And so, yes, this lone pair is participating in aromaticity. Let's take a look at the next one. Okay, so again, if you're like, I still don't understand, right? The question we're asking ourselves is this lone pair in a p orbital or no? Right, this nitrogen has 1, 2, 3, 4 regions of electron density. You've got two possibilities. Number one, it could be sp3, or it could be sp2, and that lone pair is in a p orbital, because then you'd have a continuously overlapping system of p orbitals. So the question is it in a p orbital? Let me put this here. We'll just imagine if it is, okay? So there we'd have a continuously overlapping system of p orbitals. Would it be a Huckel number of electrons then? Yes or no? Did anybody answer that? It would be no, right? It would not be it would be 4n, right? Because you'd have 4n where n is equal to 2. And so, right, Tiana, you might say, well, this compound is anti-aromatic. You might say, hey, this is anti-aromatic. It's not anti-aromatic, because remember, a compound's going to do whatever it can to avoid being anti-aromatic. And so this is going to adopt an sp3 hybridization. And so the compound is actually non-aromatic. Okay, let's look at the next one. Remember, if you have a lone pair and a double bond, they both can't be participating in resonance. Only the double bond can be. Okay, so we have an sp2 hybridized carbon here. So we have pi electrons here, pi electrons here. And then if we imagine one of these lone pairs as being in a p orbital, we have a continuously overlapping system of p orbitals. Do we have a Huckel number? Yes, 4n plus 2, where n is equal to 1, and therefore this compound is aromatic, so this would be sp2, and the answer is yes, sir. All right, and then we'll look at one more, okay? This one here. Is this lone pair involved in aromaticity? The answer is no, it can't be, because we can't have, right, the hybridization of this oxygen is 1, 2, 3. Right? It's sp2 hybridized. You've already got the p orbital participating in making this pi bond right here. Therefore, the lone pair must be in an sp2 hybrid orbital. It's not got nothing to do with aromaticity whatsoever. So maybe I should draw this around here. So the lone pair is actually in an sp2 hybrid orbital, and so the answer here is no. All right, there we go. Boom shakalak. Not too bad. So there you go. That kind of covers the section on aromatic heterocycles. There's a little blurb here about polyaromatic compounds, polycyclics, where you have a bunch of rings fused together. These are some very common ones. Naphthalene and anthracene. I think it's a good idea to have the name of naphthalene memorized. You can see that these all follow Huckel's rule. Here we have a total of 10 electrons, or 5 pairs. Here we have a total of 14 electrons, or 7 pairs. Same thing here, we have 14 electrons, or 7 pairs. And so these compounds are all considered to be, or are all aromatic. And what's interesting about these compounds is if you look at the heats of hydrogenation of them per ring, what you see is that some of them are going to be more reactive than others. For example, the center ring on anthracene is really, really reactive, and that's shown here. I'm never going to ask you any reactions with anthracene, so don't really stress about that or anything. Well, let's move on to section 17.6. We're out of aromaticity and looking at some reactions at the benzylic position. And hopefully you remember what a benzylic position is. So if you don't, if you have an aromatic ring, like a benzene ring, okay, if you go one carbon away from the ring, and then you would call that position a benzylic position, okay? So the benzylic position, you've got to have that memorized, what a benzylic position is, a carbon directly attached to the benzene ring. Okay, now it says here, recall that aromatic rings and alkyl groups are not easily oxidized. If you take benzene or just a straight alkane, like here we have 1, 2, 3, 4, so we have heptane and benzene. If you treat that with chromic acid, so hopefully you remember this from from Organic 1. This is You know, when you mix sodium dichromate, sulfuric acid, and water, what that does is it forms chromic acid in situ or in place, is what we call that. All right, and you get no reaction. However, here's where it gets interesting and what's going to be pertinent for us in this chapter is if you have a benzylic position with at least one proton on it. So here we have 2 protons, and you treat that with chromic acid, which is formed by mixing sodium dichromate, sulfuric acid, and water. Then it's going to oxidize the benzylic position to a carboxylic acid, and so you end up with some kind of benzoic acid derivative. Okay, in this case, we're making benzoic acid, and if you're sitting there going, where does this part go? Okay, well, that goes to kind of what we call compound heaven, and I'm being facetious here, but that part is completely excised from the molecule and just gets put into the waste. So don't worry about that part at all. It just gets completely removed. Now remember, you've got to have at least one proton at the benzylic carbon. And so if you do, all compounds go to heaven, right? If you don't have a benzylic proton, then it will not undergo any kind of benzylic oxidation. Besides doing it in chromic acid, it can also be done in with potassium permanganate, which is a basic condition. And so instead of making benzoic acid, you first end up with potassium. So you'd call this potassium benzoate. Okay, oops, benzoate. And then you would treat that with aqueous acid in order to protonate it. So first step, potassium benzoate, and then the second step would be protonation with aqueous acid. So this is a 2-step process here. All right, so what else can you do with a benzylic position? If you remember allylic bromination, a benzylic position can also undergo a bromination, except we call it a benzylic bromination instead of allylic bromination, and it's a free radical reaction. So if you don't remember this reaction and you want to review it, that's found in chapter 10 in the textbook. So if you need to go back and look at that, then go ahead. So we would call this compound, we would call this a benzylic bromide, right? You have a bromine at the benzylic position, and it turns out, and this is where it gets really fun, is that benzylic bromides are really useful in organic synthesis. Okay, they've got a whole holy host of uses. You can use them for SN1 reactions, SN2 reactions, elimination reactions. You can imagine where we're going with that. We're going to take a look at them. And so let's take a little journey through some of the reactions at benzylic positions. Look, if you've got a tertiary, if your bromide is on a tertiary benzylic carbon, so this carbon is attached to 1, 2, 3 carbons like that, that can undergo an SN1 reaction like nothing, okay? It works extremely well, and you can imagine why it does, because if this bromine leaves as a bromide, what do you get? You end up with a benzylic carbocation, right, which has a whole holy host of resonance structures that you could draw. So since the benzylic carbocation is really stable, that's why the bromide has that propensity to leave. Then water can come in as a nucleophile. You can do a proton transfer, and you can end up with a benzylic alcohol derivative. That's what you would call this guy here, a benzyl or a benzylic alcohol derivative. Anyhow, if you have a primary benzylic bromide, so if you only have one carbon attached to the benzylic carbon, this compound actually has a name. It's called benzyl bromide. It's not a bad idea to know the name of this compound because it shows up a lot in this class. Well, that's going to undergo any kind of SN2 reaction really well if you have a good nucleophile. Right? It's a very powerful electrophile. It's not sterically hindered. And so if you treat that with a strong nucleophile like sodium hydroxide, you can't do any elimination reactions because there's no beta proton. And so therefore, you're going to get complete SN2. And in that case, you could make this compound. This is the true benzyl. This is benzyl alcohol. And this is going to show up several times in the course as well. So to review, if you have a tertiary benzylic bromide, it can undergo an SN1. If it's primary, it can undergo an SN2. Now it says you can also cause them to undergo an elimination reaction. Let's say you treat the tertiary benzylic bromide with sodium methoxide, which is a good nucleophile, but this is too sterically hindered for an SN2. So it could undergo an E2, right? Because you have a beta proton, right? And the ethoxide, this is just a little review of organic 1, right? This can act as a strong base, pluck off the beta proton, form the double bond, and you lose the bromide. Okay, so you end up with a conjugated system, right? You have double, single, double, single, double, single, double, right? So this is a completely conjugated system that you form. Also, you can take advantage of making that stable conjugated system. If you take a benzyl alcohol derivative and you just heat it up in concentrated sulfuric acid. If you took organic chemistry 1 with me, you might remember me calling this my favorite reaction or one of my favorite reactions. I like things that are simple, and this one, if you just heat it really hard with sulfuric acid, it's going to eliminate water and form the most stable alkene. And again, you have a completely conjugated system here. So that's why it's has a propensity to form this compound, which would be technically a styrene derivative, wouldn't it? So based off of that, you can see that we can do all kinds of manipulations at the benzylic position. We can oxidize to make a carboxylic acid. We can do a radical bromination to form a benzyl bromide, a tertiary, a primary. We can do SN1, E1, SN2, E2, etc. And then when you form an alcohol, well, we spent a whole chapter talking about the chemistry of alcohols. And then if you were to make an alkene, well, we spent an entire chapter in Organic 1 looking at the chemistry of alkenes. And we reviewed it at the beginning of this summer semester. So with all that in mind, let's take a look at this here. It says, draw the expected products that you would form when each of the following is formed with chromic acid. Now remember that chromic acid is H2CrO4, but we get that by mixing sodium dichromate, sulfuric acid, and water. Sulfuric acid, and water. And there we go. So there we go. So we're going to use the same reagents every time. Well, on the first compound, which is toluene, we have one benzylic carbon. It's got at least one proton on it. And so that's going to get oxidized to give us benzoic acid. In the second one, we have two benzylic carbons, one here and this one over here. They both have a benzylic proton. And so those are both going to get oxidized to give us this compound. This is called isophthalic acid. The name is not important at all, but in case you have an inquiring mind. So this is isophthalic acid. And the last one, we have a benzylic proton here. We have a benzylic proton here, but we don't have one here. And so nothing's going to happen to that tert-butyl group. And so we're going to end up with this compound where we have a carboxyl group here. I'm just going to draw a condensed version over here, and then the tert-butyl group remains intact like that. There we have it. Okay, I think we're on to the very last section of new material for us. Let me just double check here. Kinda. One more section of chemistry, and this deals with the reduction of benzene. So let's just take a deep breath. Okay, this is our last big section. The very last section covers a little bit of spectroscopy, so nothing really new there. Okay, let's see. First thing, if you've ever wondered, can I hydrogenate benzene? Yeah, you can, but you've got to put it under really high pressure. 100 atmospheres, that's 100 times atmospheric pressure, and a high temperature of 150 degrees Celsius. I'm just going to say no thank you to that reaction. That doesn't sound like fun at all to me. That sounds like just horrible. 150 degrees and 100 atmospheres, it sounds dangerous too. Okay, so you can hydrogenate it if you hit it with a big enough hammer. So if you're wondering, well, what would happen if I took a compound like styrene? So remember, this compound is called styrene. If you treated that with hydrogen in just 2 atmospheres, which is very achievable in the lab, that's only going to hydrogenate the double bond outside of the ring, right? Because it's so much more sensitive to hydrogenation, whereas you're not going to destroy the aromatic ring, right? You're not going to start hydrogenating those double bonds because then it would lose aromaticity. So you can kind of do a regioselective hydrogenation. Now, there's a new reaction in town, okay, called the Birch reduction. Okay, it's named after a chemist by the name of Arthur Birch. And you might remember the dissolving metal reduction of an alkyne, like where we took something like 2-butyne and then we treated that with sodium in liquid ammonia. Sodium in liquid ammonia. There we go. I'm sure everybody remembers this reaction. You make a transalkene like that. Well, this is similar because we use sodium metal and it donates an electron. And we're going to take a quick peek at the mechanism. But the idea is that you make a compound that's a diene, but it's a non-conjugated diene. Could anybody tell me, would this compound be aromatic, non-aromatic, or anti-aromatic? And it's not a trick. I detest trick questions. Yeah, it's non-aromatic, right? Thanks, Audrey. All right, it's not aromatic. Why? You've got 2 sp3 hybridized carbons, for Pete's sake, okay? sp3, sp3. That was just kind of a test. Okay, so if you're wondering, why does it reduce, the 2 carbons on opposite ends of the ring, right? 1 and 4, like that. The reason why is because when you donate the first electron, and I'm never going to ask you to draw this mechanism, so don't worry about it, but you end up forming an intermediate called a radical anion. So you have an unpaired electron here, and then you have a pair of electrons here. So those get as far away from each other as possible. And then we do a proton transfer. Then it donates another electron to form another anion, and then it ends up getting protonated. So that's the Birch reduction. But if you think about having a negative charge, right? You probably noticed that you have a negative charge at this point in the mechanism, and then you have a negative charge at this point in the mechanism. So if I draw the ring, okay, let me just point it here. You end up with a negative charge here at some point and here at some point. So what kind of groups stabilize negative charges and what kind of groups destabilize negative charges? That's going to have an effect on which bonds get or which carbons get reduced and which ones don't get reduced. So let's take a look here. It says, note that Birch reduction doesn't completely reduce the ring. It has sp3 hybridized carbons and they're on opposite ends of the ring. And remember, those are the ones that had an anion on them at some point. All right, so I want you to keep that in your mind and think about, what if you had an R group, okay? Just the presence of a simple R group that is an electron donating group. Remember that alkyl groups are electron donating via hyperconjugation. If you don't remember that, that's covered in chemistry 3101. And so if you have an R group on the ring, since an R group donates electrons, the carbon that's attached to it is not going to have a propensity to be reduced because it's not going to be comfortable taking on a negative charge. You've already got something dumping electron density into there. So wherever you have an R group, it doesn't get reduced. However, what would happen if you had an electron withdrawing group, something that removes electron density? Well, that is the carbon that's going to get reduced because it's going to be comfortable having an anion, right? Because if you can imagine having, and I'm just going to scribble this down here very quickly, you can imagine that if you had this compound and if you had a lone pair here, right, that is resonance stabilized, right? I'm not going to draw the resonance form, but it is resonance stabilized. And so that's why we end up reducing the carbons that have the electron withdrawing groups on them. And if you have an electron donating group, it is not going to be reduced. Okay, so with all that in mind, let's turn our attention to question 17.18 and see if we can solve some synthesis problems here.